This is shuttle launch control at T-minus 3 hours and holding. We are counting down toward today's launch of the STS-56 mission, and all is proceeding on schedule here in Firing Room 3 and also at Launch Pad 39B. Liftoff of Discovery's 16th trip into space is planned for the opening of today's launch window at 1:29 a.m. Eastern Time. The window for today's launch extends for almost 2.5 hours. Weather conditions continue to look favorable for an on-time launch at 1:29 a.m. And we have the flight crew for STS-56 getting into their launch and entry suits. Commander Ken Cameron is being assisted getting into his boots. Crew is making the second attempt today. They reported earlier after the weather briefing that they were ready to go. Mission Specialist Mike Foale. He's flying for the second time today. He flew on the first Atlas mission, and of course today is the second flight of the Atlas payload. Pilot Stephen Oswald. He's flying in the shuttle for the second time today, and will be involved in helping the orbiter make the over 140 maneuvers required for this particular mission. Crew is getting the last minute items stowed into their suits that they'll be using. This is Mission Specialist Ellen Ochoa. She'll be using the robot arm to deploy the Spartan satellite, Spartan spacecraft, and will retrieve the Spartan and put it back in the orbiter's payload bay, and it will come back to Earth. This will be Dr. Ochoa's first flight aboard the space shuttle. And we have Mission Specialist Ken Cockrell. He's also flying aboard the shuttle for the first time today. This is shuttle launch control. We have the STS-56 flight crew members leaving the crew quarters at the operations and checkout building. Pilot Stephen Oswald, Commander Ken Cameron, Michael Foale, Ellen Ochoa, and Ken Cockrell. The primary payload for this STS-56 mission is Atlas II. It is the second in NASA's series of atmospheric laboratory for applications and science space lab missions. We will be showing you live coverage of the astronauts as they enter into the White Room and as they are assisted in getting into the rest of their gear for the flight today. T-minus 2 hours, 37 minutes and counting. This is shuttle launch control. This is a close-up shot of the hydrogen flare stack located at the pad perimeter, inside the pad perimeter. Hydrogen vapor that is vented off from the external tank as the loading operation continues and the topping off phase continues. That propellant is vented off at through that flare stack and away from the vehicle. The flight crew will close and lock their helmet visors in the next few seconds.
ATC TLT, fashion warning memories clear, no unexpected faults.
Copy. Flight crew, close and lock your visors and initiate O2 flow.
Flight crew out.
15.
T-minus 10, 9, 8. We have a go for engine start. 6, 5, 4, 3, 2, 1. We have ignition. We have liftoff of Discovery on the second mission to Planet Earth research flight.
Houston now controlling. Discovery is underway, and it's rolled on course for a 57-degree orbit. Three engines on board Discovery now throttling back to 2/3 throttle to prepare the spacecraft to pass through the area of maximum air pressure and go supersonic. Discovery now traveling 1,000 miles an hour, 3 miles east of the launch pad, altitude 6 miles. Good solid rocket booster separation is confirmed. This is Mission Control, Houston. Discovery is currently passing above the northeast coast of Australia, just along the coast that holds the Great Barrier Reef. Now moving into view is the Spartan 201 platform. On that platform that will be deployed using the mechanical arm on the 4th day of the flight are mounted instruments for the solar wind generation experiment, which will explore the velocity and strength of the solar wind as it flies free from Discovery for a little more than 2 days.
Okay, payload retention logic powers. Those 2 arms. Okay, about to go free drift here, guys.
Discovery Houston, when you get to the next stage, we have no updates to the deploy plan.
Don't thanks. Willie. Thank you, Jay. 57 and 28.
Okay, we're doing great. We're just about on time.
What does it say?
Or we're ahead of time, really.
Point. It's at the end of the
This guy.
We've got event timers. We're in attitude.
Standby. Mark.
Okay,
Lost ridge.
Got D-ridge.
Have D-ridge.
Open. Back
Open.
Out. Back out slowly.
I see you separating.
How to go. You just about through the pan.
Real nice.
You're clear.
Real nice. Clear.
Spartan release.
Okay.
All right. Let's go. Another couple of
Houston, we have Spartan release.
Wow, look at that picture. I don't know what land we're going over.
It's awesome, isn't it? I just
Spain?
No.
What is it? Doesn't matter.
It's France. We might go over France.
It's 143.
okay. We're looking for 203 for the start of the maneuver, right?
10 seconds.
Is it pirouetted?
Not yet.
Okay, it's supposed to start in 2 seconds. Let's see. It's not pirouetting. There it goes.
Yes, it is.
Okay, it started. Oh, let me call.
Yeah, go.
Listen, Discovery Spartan started its program.
Now receiving live television from Discovery, just showing the Spartan platform 45 feet away. Discovery just moving into nighttime. As it heads out across the Pacific Ocean on a northern track that will take it across the coast of the northwest United States. This view from a camera mounted at the end of Discovery's mechanical arm as it approaches the Spartan platform and the grapple fixture on the arm. In view is the fixture on which the arm will be placed and locked on to retrieve Spartan. Commander Ken Cameron studying Discovery as the CHOA prepares to grasp Spartan with the mechanical arm. Cameron's now switched off Discovery's automatic steering jets. Put the spacecraft into a mode known as free drift so that no steering jets will disturb the arm as it grasps Spartan. And Ochoa now moving the arm in toward the satellite.
Houston, we show a good grapple.
That is a very pretty picture we're still looking at down here.
Houston Discovery, we've captured Spartan.
Great work, Ellen.
What I wanted to talk to you about today was one of the Atlas instruments called SOLCON, which stands for Solar Constant. But before I describe that, I'd like to talk a little bit about how it fits into the whole Atlas payload. And I must say it's a little bit hard to keep my concentration because I'm looking out the aft windows at some great views of South America right now. But we'll continue to look. We're in an attitude right now where the payload bay is facing the sun. And that's because several of the instruments on Atlas are specifically measuring the sun. And the reason for that is that Atlas, as you know, is studying the Earth's atmosphere. And what we're trying to find out is what chemicals are present and in what altitudes and what affects the concentrations of those chemicals like ozone and other molecules. And we want to be able to distinguish between human activities that might affect our atmosphere and natural effects that affect our atmosphere. And of course, the sun is the primary source of energy for the Earth and its atmosphere, and that's why it's important to be measuring the sun in order to understand our atmosphere. So for the last few hours, we have been in a position where several of the instruments on Atlas are looking at the sun, and one of these is SOLCON. And what SOLCON is measuring is really the total energy or the total amount of radiation that's coming from the sun. And the reason it was called a solar constant is for many years people thought that that value never changed. It was always the same. But recently they've realized that it does change, and it changes about in an 11-year solar cycle where it goes from a maximum to a min and back to a maximum. And the total amount changes maybe by about 0.1%, which doesn't sound like much, but even small changes in the amount of energy reaching our atmosphere has the potential to have much bigger changes on Earth in the climate or on human health or on other life forms in health. So that's the reason that's important to get precise measurements of this radiation. And it's also important to measure this quantity above the atmosphere because the Earth's atmosphere absorbs radiation from the sun, and it absorbs more in some parts of the solar spectrum than in other parts. So in order to get a very accurate value, we must be above the atmosphere, and that's why the shuttle is a very good tool for using this instrument. SOLCON is an instrument that is sponsored by Belgium, and is one of several of the Atlas instruments that is sponsored or co-sponsored by scientists in the European community. So Atlas really is an international payload. There are American, Swiss, German and Belgian scientists all involved in studying the atmosphere. Just to tell you a little bit about how SOCON works, it basically has two cavities, and during its measurement-taking periods, one of the cavities is open to the sun, and it's black, and therefore it absorbs the energy from the sun and heats up. The other cavity is electrically heated. It's not open to the sun, and it tries to maintain the same temperature or heat flux as the cavity that's open to the sun. And by measuring how much heating is required to maintain that, they're able to obtain a very good value for the amount of energy coming from the sun. One of the important aspects of this instrument, as well as the other Atlas instruments, is that they're calibrated very carefully before we fly and after we fly, and also as we fly. We're not always in a mode where it's taking measurements. In some of the other orbits that we're in, there are actual calibration equipment inside the instrument that are checking to make sure that the instrument does not degrade while we're up, or if it does, they can at least characterize how it might be changing. This is the second flight of Atlas, so we have some data of the solar constant from last year. We'll get some this year, and then in subsequent Atlas flights, we'll be able to get more measurements, and that way we'll be able to plot out the change in the solar constant over the solar cycle. Once we have a better idea of what that value is, we'll be able to say more about whether the sun is making some of the changes that we see in the atmosphere, or whether it's due to human activities, and that will give us a chance to understand how to change that. I'm not sure you'll be able to see this, but I've put a diffraction grating up in the window because the sun streaming in through the overhead windows is so bright, and you might be able to get a little bit of the spectrum as I put it here. I don't know if that's washing out on your cameras or not, but it's very, very bright here. Very bright purples and blues and green and yellow and red. It's really a pretty sight here to be in this attitude with the sun streaming in through the windows as we orbit the Earth. One of the other instruments on board, which we'll be talking about later, is very similar to SOLCON. It's also measuring the solar constant, so we'll have actually two independent measurements of that on this flight, and that will help the scientists have a lot of confidence in the data and also be able to compare it to similar instruments on longer-term satellites. And I think that's about all we have on SOLCON for you today, and we can get back to you later on some of the instruments later in the flight.
Well, good morning. My name's Michael Foll. I'm a mission specialist on the Space Shuttle Discovery, and we're flying a mission called Atlas II. What I want to tell you about today is a particular experiment on Atlas II called MARS, or its acronym stands for the Millimeter Atmospheric Sounder, Millimeter Wave Atmospheric Sounder. We'll show you out in the bay later on what that instrument looks like. It's basically a radar that can receive only radio waves that come from a particular molecule that occurs in very, very small quantities in the Earth's atmosphere. It's called chlorine monoxide. And I have a little story to tell you about how chlorine monoxide could be damaging the ozone that protects us from ultraviolet rays. We launched from Florida north, and we flew up towards the North Pole. You can see it basically as we come up the United States. We come up over the North Pole, or 57 degrees north to be exact, then sweep on down. We rise up towards the North Pole. We catch sunrises and sunsets, which other instruments on Atlas are looking at. However, Mars is actually looking out across the horizon towards the wind that revolves around the North Pole. And I want to tell you a story about chlorofluorocarbons. I'm sure you may have heard of these on the news. And also you know that they're part of the refrigerant that's used in your car, in the air conditioning unit. Here is a chlorofluorocarbon molecule. See it floating here in space. The green things are actually fluorine, and the yellow is chlorine, held together with a carbon atom right at the middle. And what happens is that sunlight, which is actually illuminating my face quite brightly at the moment, comes in and breaks this molecule apart high up in the atmosphere here. A chlorine radical, or just a single chlorine atom, and then the debris of the chlorofluorocarbon just kind of floats away, just as you see it there. But anyway, then we have this chlorine atom floating around in the free space above the Earth's atmosphere, mostly actually in the stratosphere. And it meets the precious ozone molecule that's made up of these red atoms. These are red oxygen atoms. It takes 3 of them, and it makes an ozone molecule. Anyway, here comes a chlorine radical, and it captures the ozone. You see it's joined up there briefly, only very, very briefly, with the ozone. And then immediately after that, it breaks apart. Leaving you with an oxygen molecule and a chlorine monoxide molecule. Chlorine monoxide is the red and yellow molecule here that is being emitted by Mars. And you can see the oxygen molecule is just disappearing by my head. Anyway, the story hasn't finished. Along comes another oxygen atom, which happens to be floating around in space here, together with the oxygen molecules and the ozone molecules, and the chlorine monoxide attacks it. As you can see, chemistry in space is slightly tricky. But here we finally got chlorine monoxide, the oxygen atom, and turned it into oxygen, leaving a free chlorine radical floating around again. And all this trouble was caused by the chlorofluorocarbon in the beginning. We still got the chlorine hanging around, we broke up ozone, and we made some oxygen molecules. So to summarize, basically Mars is an instrument that's particularly looking at chlorine monoxide, the joined up red and yellow molecule. And that molecule is an indicator of how much chlorine has come from the chlorofluorocarbons that has been put into the atmosphere by our refrigerants and other sources. So it's important that Atlas 2 do this survey for about 8 days, 7 days, monitoring how much chlorine monoxide has developed in the northern latitudes. And that way we will know how much of an ozone hole could be caused by this particular molecule. That's all for the Mars explanation.
Using temperature data, MOS can help determine the rates of chemical production and ozone loss in the upper atmosphere. The investigation uses an antenna, which can be seen now, which scans Earth's atmosphere to collect spectral information at different altitudes. Millimeter wave radiation coming through the atmosphere enters the steerable antenna, which is moving even as we speak, which consists of a 3-foot diameter main reflector and a smaller sub-reflector, and the radiation is then focused into the MOS receiving electronics. Both temperature and ozone concentration will be measured this way, and both are important for a number of reasons.
Right now, we're in an orbit where we have the payload bay facing towards the sun. That's because several of the Atlas instruments are measuring energy coming from the sun. And that way we'll be able to have a better idea over the series of Atlas missions of how much of an effect the sun has on our atmosphere as opposed to human activities in changing our atmosphere. One of the instruments that is in the bay looking at the sun is called SolSpec, which stands for Measurement of the Solar Spectrum. It's a French instrument, one of several of the Atlas instruments that are sponsored or co-sponsored by international scientists. What this instrument does is separate the sunlight into the different wavelengths and then measure the amount of energy in each of these different wavelengths. Normally we think of just the visible light coming from the sun, and we can use a piece of a prism or a diffraction grating like I have here to separate that light. In fact, if I just put it up here in this overhead window, we'll be able to use it to look at the different colors coming in from the sun. You can see them in this spectrum right here. Well, the Sol Spec instrument has something very similar to that diffraction grating, only more sophisticated, and it's also looking not only in the visible but in the ultraviolet and infrared as well, and measuring the amount of radiation in all the different wavelengths. It also calibrates itself every day on orbit, which is very important for these Atlas instruments because the ultraviolet light coming from the sun degrades the optics, and in order to get the most precise and accurate data, we need to constantly be checking and making sure that we're making the most accurate data possible. So in addition to checking the instrument before and after flight, it's doing it during the flight as well. There's another Sol Spec instrument that's up on a satellite called Eureka, which was deployed from the shuttle on a shuttle flight last year, and it's going to be picked up on STS-57 next month. And that will also provide an independent set of data which can be compared to the data that Sol Spec on Atlas is getting.
One of the questions that I'm always asked is, what can you see from orbit? A lot of people have the mistaken impression that when we're up in space that you see the world as a blue marble like they saw from Apollo. And I try to explain to them how close you are when you're only 160 miles above the Earth. So why don't you just describe some of the things you can see in the way of cities and city lights, lightning storms, any of that stuff?
Well, you really are a lot higher in terms of perspective, as you know, than in an airplane. And so we can actually see about 2,000 miles from this point out towards the circumference of the Earth all around us. And the Earth is a large but definitely discernible ball above us at the moment. When I say above, of course, that's relative to me. In that sort of 2,000-mile radius, we can see at night thunderstorms flashing. And in fact, one of the most interesting things about the thunderstorms is that they seem to go off simultaneously many, many, many hundreds of miles apart, which in fact is quite incredible, since they must be triggered by the speed of light, by radio waves rather than by sounds, so it wouldn't travel that distance in such a time. The other things we see are cities at night. Taco, on my shift here, has been using an image intensifier in conjunction with a camera called Hercules that allows him to take pictures of cities at night and during the day, and then send those pictures to the ground so that people on the ground can get very high resolution, high definition pictures immediately of what we've just seen.
Let's see. When do we next pass over land? Not for a long, long time.
Coming into view now from the camera located at the middle joint of the mechanical arm is the continent of Australia. As Discovery moves 160 nautical miles above it. This is Mission Control Houston. This view from the Shuttle Discovery showing Houston as it passes overhead on a very clear night, looking down at the Texas Gulf Coast and just having passed over Houston. now as it moves on up the Gulf Coast.
This is Mission Control, Houston. Discovery is currently making a swing from the northwest to the southeast across the continental United States. The orbiter's currently moving about 80 miles or so west-northwest of Cedar Falls, Iowa, making a pass down from there through the southeastern portions of the United States, heading out across the Atlantic Ocean, crossing the coastline somewhere around the coast of Georgia and Florida. In the cruise timeline, Commander Ken Cameron is scheduled to be conducting a ham radio call very shortly with the Tishomingo County High School. That's in Luca, Mississippi. And that is coming up very shortly as the orbiter moves within range of that area of the country. Southern tip of Florida now visible from Discovery as the orbiter's moving just a little to the west-northwest of Cape Coral, Florida. The Keys down near the southern tip of Florida, clearly visible from Discovery. The city of Miami on the southern tip of Florida. This is the 101st orbit of the mission of Discovery.
This view looking back from Discovery as it continues out across upper Canada now. Discovery will continue across Hudson Bay and then off the coast of Newfoundland. Discovery now continuing.
Discovery Houston, 1 minute switching over to the East Tidris, and we're seeing a beautiful view of what we think's the aurora out there. How's it look out the window?
Jay, we're missing it. We're all downstairs in the mid-deck reconfiguring things and getting the last jobs done before the redshift goes to sleep. We'll have to take your word for it.
Roger that. We'll see you on the other side.
Discovery above Canada as it television cameras pick up the northern lights. Television is from Discovery as it heads out across the Mediterranean Sea.
Inco Flight, where are we on everything? We got the SPCs up, and we got the MABs running. Everything's going.
Everything's complete.
Thanks, sir.
T0, SRB ignition.
Liftoff confirmed.
Thank you.
Roll program, Houston.
Roger, roll, Discovery.
Throttle up, 3 at 104.
What throttle up?
Discovery, go at throttle up.
Roger, go at throttle up.
SRB SEP.
103 converged.
Stand by for 2-engine tail. Mark.
Discovery, 2-engine TOW.
Roger.
Single engine Zaragoza 104.
Discovery, single engine Zaragoza 104.
Roger.
Like you said, we got a line problem. Meter, we're checking.
Copy that. That way we hide the echo.
Discovery Houston, we show a nominal MECO, no ohms 1 required, and you have a go for the photo DTO.
Roger, we concur.
Flight payloads, we got all good, ready for launch indications also.
Okay, good. You see no reasons why we shouldn't be unberthing.
Flight payload sees none.
PDRS is still go.
Okay.
We're just a few inches away, flight.
Copy.
And we are at low hover. Brakes are on.
All operators, a reminder, in 2 minutes I'll come around the room for a go for release. All operators, I'll be going around the room for go for deploy. Prop.
Go.
GNC. Go. FIDO.
Go.
Rendezvous.
Go.
GPS.
Go.
Payloads.
Go.
Okay, Eagle and ECOM, our systems are all looking there. Good there?
Go. We're go.
Okay. INCO? For go. PDRS?
Go.
Okay, FAO, we have any loose cleanup items?
No, sir, I'm just watching for steps in part 2 of this procedure.
Okay. Capcom, they got to go for deploy.
Discovery Houston, your go for Spartan deploy.
Roger, go for deploy. Thank you.
Discovery, 2 minutes to hand it over to the East Tetris.
Spartan
Houston, we have Spartan release.
We copy.
GNC, attitude check.
1.4 degrees out at release.
Flight pilot, looks like he's got a good burn.
Copy that. Burn report prompt. And Rendezvous Fido, you happy with his burn?
Flight Rendezvous, yes, sir. And Flight Fido, I'm real happy.
Okay, we're on the way in.
Yes, sir.
Discovery Houston, we saw a good TI burn. We're about a minute from losing you through Diego, and we'll pick you up on the west satellite at 2355.
Roger that, and we'll take the T1 TIG as it comes up on the spec.
And we've been real happy with your laser data, showing about a 20-foot delta between that and the radar.
Roger, and some of that may be time delay on the call.
And we concur.
Nice work, Inco. And PDRS flight, arm status is go.
Arm status is go. We're standing by.
PDRS flight, is that, that's not arm motion either, is it? That's,
No, sir, that's all piloting right there.
okay.
I'll report as soon as I see arm motion.
Ready to go momentarily.
Capture in progress flight.
That is a very pretty picture we're looking at down here.
And PDRS flight,
Good grapple flight.
or grappled and rigidized.
Yes, sir, secured.
Captured Spartan.
Great work, Alan.
Flight Rendezvous.
Go, Rendezvous.
We're there. My compliments to the crew.
Yes, sir. That goes for all of us there, Capcom. Good job.
And Discovery Houston, there's a lot of smiles in the room down here. Congratulations on a fantastic rendezvous and grapple of the Spartan.
Okay, we show 5 of 6. We have 3 on the B side, so we do
That's
have good
great.
ready for latching.
Nice work.
And there's the
Ah,
sixth
there's
one.
all 6.
We think we're there, Houston.
Concur.
We concur. Nice work. That was a real good thought, changing the reference frame. That worked slick.
Yeah, she's a smart lady.
That's the truth. It sounds like you're all working as a great crew together. It sounds great from down here.
Okay, but
He feels the hack turn is not, if we get the information to Ken, then that will solve the aggressiveness on the hack, and the getting on the hack and stay on it should be okay.
Okay. Well, it sounds like we've been able to find some energy reserve where we're losing it on the bottom, so Capcom, we got to go from the room here, and based on what we're getting from the STA pilots' reports, I think I'm go for the deorbit burn, so why don't we go ahead and give that to Ken and let him get on into the procedures.
Go ahead.
You have a go for Ops 302, and you have a go for the deorbit burn. And I've got some words on flying the hack and final approach whenever you're ready.
Flight Fido.
Go, Fido.
Based on the good burn, I'd like to release Edwards support and SMS support as well.
Yes, sir.
Discovery Houston, we saw a good deorbit burn.
Roger, look at that.
TACCOM flight.
So, your go for nominal drag chute deploy. A reminder to select manual speed brake, full closed at 3,000 feet, and full open after main gear touchdown.
Roger the drag chute and the speed brake.
And Discovery, your predicted normalized touchdown is 1,600 feet down the runway.
Processing the MLS.
Gear stand and lock. Brake isoles open.
Okay.
Speed brake coming open flight.
Nose gear touchdown.
Ground speed enable, auto load release.
Sorry, DPS.
Wheel stop, Houston.
Copy, wheel stop Discovery, and you got a bunch of smiling faces in the room here. That was a beautiful piece of flying, Ken. And welcome home to the crew after a super mission.
Thanks very much. Thanks very much to the whole NASA team for making this possible. It was a privilege to be part of it.
Okay, if you'll stand by, we'll go around the room and check for any post-landing deltas.
Okay, all flight controllers, LRD has taken over, and they now have control of the vehicle. GC, they want you to hang in until the command handover is complete, but they've given the go for release of the flight team.
Discovery Houston.
Go ahead, Houston.
Andy, we're going to be signing off. If you've got good comm with OTC.
Okay, I copy that, and we'll be turning it over to the SCOs here also. Thanks.
Okay, we'll see you back home.
This is Kennedy Space Center Shuttle Control, watching a sunrise here at Kennedy Space Center where things are very busy, getting ready for today's landing of Discovery, ending the STS-56 flight.
Discovery Houston, on energy approaching the hack. No change to weather. Winds are 310 at 5, peak 8. Your go for nominal drag chute deploy. A reminder to select manual speed brake, full closed at 3,000 feet, and full open after main gear touchdown.
Roger the drag chute and the speed brake.
Discovery is approaching waypoint 1 at the point at which it begins the heading alignment turn.
Discovery on energy at the 180.
Energy is looking good as Cameron brings Discovery home around the heading alignment turn.
Discovery on energy at the 90.
So far, Cameron's right on the money. Everything's looking good. Range to the runway 8 miles, altitude 15,000 feet, sending at a rate of 200 feet per second. Discovery is now processing microwave landing system data, refining its sense of its course to the runway.
Discovery on and on. Final wind check 310 at 5, peak 8.
Roger.
Discovery's on glide slope and on center line, reaching for runway 33. A range of 5 miles, altitude 8,600 feet, descending at about 140 feet per second. Discovery is beginning to flare a little bit, taking some of the steep angle out of the angle of approach, beginning to induce drag and slow the vehicle as it approaches the runway. Range 3 miles, altitude 4,800 feet. We're seeing final flare. Should see the landing gear coming down shortly. Main gear is down and locked. Main gear touchdown. Standing by for drag chute deployment. Chutes deployed and the nose gear is down. Discovery's crew returns with a bounty of new knowledge of the sun, our home planet, and its fragile atmosphere. Discovery rolling out on runway 33.